Okay, we're live. Once again, we are here. We are live, and it is time for lecture. As usual, I am going to take some time. I'm going to ramble a little bit just to give people time to arrive. Uh, you know how it is. Like sometimes people have another class halfway across campus and it takes them a while to get there. Sometimes people get lost in the very, very confusing mess that is Point Pleasant University's campus, all of that stuff. So I think it's a very good idea to just take a little time. Anyway, welcome. It is Wednesday, my dudes, I believe is the phrase that sometimes people will use. And today is the second to last lecture before I have to take a little hiatus from lecturing. I've had a very, very long day today. I taught various classes already, and I have been up and working for much longer than I normally would be. So I apologize if I am a little off my game today. I will do my very best to give y'all the best lecture that I possibly can. But here we are. This is the world that we are working with. So we are going to try real hard to do a good job, but my brain is not firing on all cylinders at the current moment in time. Let's put it that way. Hopefully, though, we'll be able to make it through this. So let's see. Last time we talked about probability, and we largely talked about biases that human beings and other living cognizant creatures have when it comes to thinking about probability, because our brains are not really wired to think about probability. And we talked about the gambler's fallacy, so the mistaken belief that past random events will influence future random events. We also talked about just the likelihood of things happening in general, what makes something a particularly unusual outcome. We set a cutoff of it for a number to be unusually high or unusually low. It has to be 1.96 standard deviations above or below the mean. And at that point, you are either higher than something like 95% of other people on a metric or lower than 95% of people on another metric. You are in the top or bottom 5%. And that makes you very unusual. That's a very unusual thing to happen. And we would consider something significant if there is a less than 5% chance of getting that just by coincidence. That's more or less what we went over on Monday. For our next trick, we're going to talk about probability and samples. So let me just move us on over to the lecture slides. Boop, boop, boop. We here? Think we're here? All right, I may have to make myself smaller at some point during this, just so you can see the slides a bit better, but let's get rolling. So first off, let's talk about the concept of sampling error. We mentioned this before, I think maybe in the first lecture, one of the first few lectures, and we mentioned that the first problem of working with sample data is that oftentimes we are trying to use a sample or a small subset of people to draw conclusions about a population or the entirety of humanity or the entirety of a certain group of people or of a certain type of people or people with a certain illness or people with a certain type of belief. And no sample is ever going to perfectly represent a population. There will always be some difference between the full population and the sample that we've pulled from the population. And that difference is called sampling error, because often we're trying to use the sample to draw a conclusion about the population. So far, we have been talking as if we have the entire population. So let's say we have a research question, and that's great. And we look at the population and use that to answer that question. So incredible times, we have the entire population and we are using that to draw a conclusion. But wait, how often do you think it is actually possible for us researchers to get data from every single person or every single incidence of whatever it is we're studying? How often do you think that researchers have population data? Well, a reality check, we pretty much never have population data. Like I said, it's very, very, very difficult and resource intensive to get a lot of participants, much less the entire population that you're interested in. For example, say everybody with major depressive disorder, or every human being on the planet, or records from every single government that has ever existed, things like that. So oftentimes we are working with sample data. We're working with a small subset of the total population that we care about. So far, I have been talking as if we have population data. We talked about population distribution of scores. We've talked about z-scores, which you need population data to calculate. And we've talked about finding the probability of a score in a population distribution. We rarely actually can do these kind of things because we rarely actually have population data. So why did I bother to talk about it? Why did I tell you any of this stuff? Well, we're going to talk about how we can use samples to draw conclusions about populations, and a lot of the logic that we're using is pretty similar. Of course, we do need to tweak it because we don't have every single person in the population, and we know our sample is going to be different from the population, you know, the whole concept of sampling error. But we're going to use that information. We're not just tossing it out. So first off, let's talk about how a group of samples make up a distribution. This is relevant to how we can draw conclusions from samples that we can apply to populations. A group of samples, if you take the means of a whole bunch of samples and create a distribution of all of those sample means, this creates something called a sampling distribution. A sampling distribution is a distribution of statistics, which can be means, they can be standard deviations or variances, but it's a distribution of statistics obtained by selecting all possible samples of a specific size from a population. So say, every possible combination of 50 people from the entire human race. Now remember, samples, we're trying to use these samples to draw conclusions about the entire population that they come from, but we know that the sample is going to be different from the population. There's a lot of reasons. It's because we're unlikely to get extremely high or extremely low values on whatever we're measuring from the population if we're just randomly selecting 30 people from our sample. Samples will be missing certain types of people. Often we'll be getting our samples from a very specific type of place that may not be representative of everywhere. So a lot of samples and a lot of psychology research has been done in what we call weird countries, Western, educated, industrialized, rich, and democratic countries. And that is not the only type of society out there. So some of that sampling error will come from the fact that our sample doesn't represent all of humanity. We have a very specific type of human being. But the nice thing about this is that generally speaking, 50% of samples will overestimate the true value of the population, whether it's the population mean or the population standard deviation. And about 50% of samples will underestimate the population mean or standard deviation or whatever you're working with. So if we get a whole bunch of samples from a single population, 50% will be too high and 50% will be too low. They'll balance out on either side of the population mean. So samples are great. They're basically what we have to do if we want to draw conclusions about the population, because there's no way we're getting the entire population. Let's say, going back to the promise, we use the promise scale, or a promise scale. So the promise is a set of scales that are used in healthcare and things like that. And we used one of these last class to sort of talk about probability. The promise scale that we used is the mental distress scale, and just as a reminder, the mean of the mental distress scale, the population mean, is 50. Now let's say I randomly select 30 people in the subway, and I test their mental distress score, so I have a sample of 30 people. Depending on which 30 people I randomly happen to select, I probably will not get a mean of exactly 50. I probably won't get exactly the population mean from that sample. The difference between the population mean, the true mean of all mental distress scores on the promise, and my sample mean is sampling error. Our goal is to try and estimate how much sampling error there is. We want to know, when we collect a sample, how close is our sample to the population? How much can we trust the results from the sample relative to the population? So that's going to lead us to create a new statistic that tries to put a number to how much sampling error we have. So let's take our example. Let's say we've got these 3 subway cars here. So each of these subway cars has, I think, about 7 people in it. And each one has a different mean. Now again, the population mean of the PROMIS mental distress scale is 50. So assuming that we perfectly are representing the population, the mean of all these cars should be 50. But they're not, because they're samples. No sample will perfectly represent a population. Some of them are close, so the first subway car has a mean of 51.57. That's fairly close to the population mean of the PROMIS. The second car has is a bit further off, as is the third car. But they're all in the general area. As another reminder, the standard deviation of the PROMIS is 10. And you can see none of these individual samples are quite at that number. Some of them are closer than others, but none of them are exactly there. Let's say we've got another 3 subway cars, and they also, their means are somewhat close to the population mean. Their standard deviations are in the general ballpark of the true population standard deviation. But they're samples. There is some error there. They are not perfect representations of the true population value. So here is a graph of all of our sample means. On the x-axis, we have which subway car we're looking at. On the y-axis, we have the mean. And their mean ends up being about 49.12. So if I average all of these 6 samples together, their mean becomes 41.92. That is a lot closer to the true population mean of 50 than most of the individual cars. But there is some error around that. Some of these samples are really overestimating the population mean. Some of them are really underestimating the population mean. So there's some variability around these sample means when we're trying to estimate the population mean. Now let's say we grab a whole bunch more samples. We get a whole bunch more cars, and we get something that looks like this. It's starting to look more like a normal distribution. But the true population distribution is a true normal distribution. It looks more like this black line here. You can see that even though we've got a bunch of samples, they're still not quite at the population. We can see that here the population mean is higher than the center of the sample means. And here we can see that our sample means here, I'd say our sample mean is on average higher than the true population mean. It's not a perfect overlap, is what I'm saying. There isn't a perfect overlap between our samples and the population. But the more samples we throw in, the closer we get to the true population. We are improving the accuracy of our estimate by collecting more samples. So, let's say I'm looking at PROMIS scores, and we know that the population distribution of PROMIS scores are normal. This is a thing. The PROMIS scales are intentionally created to have a normal distribution of scores. If I get the PROMIS scores of every single human being on Earth, it should form a normal distribution with a mean of 50 and a standard deviation of 10. Now here I have 2 distributions. Let's say these are 2 distributions, both of PROMIS scores. Assuming that the true population distribution for PROMIS scores is normal, and my samples have very little sampling error, which graph probably looks closest to my to the distribution of my sample? The distribution of PROMIS scores in my sample. The answer is A. If there's very little sampling error in my sample, then it should look pretty close to the population distribution. A looks fairly close to a normal distribution. It's not perfect, it's not, say, perfectly symmetrical, but it's close. B, on the other hand, is super positively skewed. This would be a lot of sampling error if we're talking a normal distribution. Just to remind you what that looks like, we can draw a normal distribution over both of these hypothetical samples. Normal distributions look like this. We can see A looks a lot closer to that. B, way off. There's a lot of sampling error in B. And this brings us to a concept called the distribution of sample means. And this is one of the steps to trying to estimate how much sampling error we have. That's why we're talking about it. The idea here is that if you get a whole bunch of samples from a population and average together all of their means, all of those samples means averaged together should be close to the population mean, because they're all drawn from the same population. And if you get enough sample means from the same population, those sample means should form a normal distribution. Most of the scores are in the middle, very few are very low or very high, and it's a symmetrical distribution. And the larger your sample size, so the larger chunks of the population are in each of your samples, the closer your sample means will be to the population mean because you have more of the population in your sample. The more of the population you have in your sample, the closer it's going to be to the population. Which brings us to something called the central limit theorem. The central limit theorem says that the more sample means that you have, so the more samples you have from the population, the closer you will get to the population mean. And it also says that if you get a whole bunch of sample means and create a distribution of sample means, it will always form a normal distribution. You will normally start to get a fairly normal distribution when all of the samples in this distribution are at about 30 people each. So you typically want 30 people or more in a sample. Now, why does it form a normal distribution? Well, that's because every sample has a roughly equal chance of overestimating and underestimating the population mean. And because these samples are pulled from the population, most of them should be fairly close to the population mean, but you will get some rarer samples that are way above the population mean or way below the population mean. Let's say on mental distress, if I get like 20 groups of 30 people and take each of their means on mental distress, most of them should be pretty close to the population mean of 50. They're probably not exactly at it, but they should be pretty close. But you will get some samples that are probably have very high mental distress on average and some samples that have very low mental distress on average. But most of them will be right in the middle. It should end up forming one of those normal distributions where most of the samples are fairly close to the population mean, if not exactly there. Half of them are lower, half of them are higher, most are in the middle, very few are out on the extreme ends. So let's go back to our subway car example. When we only have 3 subway cars, we average together all their means, and we get a mean of 51.57 with some error around it. That is kind of close to the population mean of 50, but we're not quite there. Now let's add in 3 more cars, so we're going to increase the number of samples we have in our sampling distribution. Now the mean becomes 49.12. It's within 1 point of the population mean, whereas before we were about 1.5 points from the population mean. So we've reduced our error, but there's still some variability around that. We still have some samples that are overestimating and some samples that are underestimating. So the more samples we have, the closer we get to the population mean, but the samples are all going to be different from the population mean and probably somewhat different from each other. Which leads us to something called standard error. Standard error is the name that we use for our measurement or our estimate, our numeric estimate of sampling error, our estimate of how different our sample is from the population. It's written like this. This is sigma with an M after it. Remember, sigma is the symbol that we used for standard deviation. This is saying this is the standard deviation of a distribution of means. Our measurement of sampling error is just, on average, how far away is a sample mean from the population mean. It's a type of standard deviation. It's specifically a standard deviation of a distribution of sample means. So the standard deviation is just the average distance of a score from a mean of a set of scores. The standard error is the average distance of a sample mean from the mean of a set of sample means. And we use that to estimate how close our sample mean is to the population. Are we very, very far from the population, or are we close to it? How representative is our sample of the population? How accurate will our results be based on our sample? Here is the formula for the standard error. It's really simple. So again, there's the symbol for it. This is the population standard error. And to calculate it, you take the standard deviation of the population divided by the square root of the number of people in each sample. So little n is the sample size that was used to calculate all the sample means, and sigma is the standard deviation of the population. This is our formula for our estimate of sampling error. So standard error, again, standard error is the average distance between a sample mean and the population mean. On average, how far off can we expect to be samples to be from the population? This is super important because, again, this is our estimate of sampling error. It's saying, on average, how off do we expect our sample to be from the population? And how much should our mean differ from sample to sample? This is used for a lot of things. Almost any type of statistic that's trying to, say, figure out if you can reject or fail to reject the null hypothesis, anything that's trying to test a hypothesis. I am not everything, but a lot of statistics used to test hypotheses, like, is the control group different from the treatment group, and things like that, use the standard error. If you're creating a confidence interval, so let's say I'm 95% confident that the true value is in this range, you're also using the standard error. We'll talk more about confidence intervals later on. Now, the standard error is determined by exactly two factors, and if you've seen the formula, you can probably guess what those are. The first is the sample size, and the second is the standard deviation of the population. How do you know this? Like I said, all you have to do is look at the formula for the standard error. The formula for the standard error is literally the standard deviation of the population over the square root of the sample size of the samples in your distribution. Of course, those are the two things that determine the standard error. Those are the two things you use to calculate it. Now, there's something called the law of large numbers, and you're probably somewhat familiar with this, like, tangentially, but the idea here is the bigger our sample size is, the more likely our sample will be similar to the population. In other words, the bigger our sample size, the lower our standard error. The bigger our sample size, the less sampling error we've got. The bigger our sample size, the more accurate our sample is to the population. And of course, this makes sense. Again, the bigger the sample, the more of the population you have. If you only have 1% of the total population, your sample might not be the best representation of the population. But if you have 99% of the population, your sample is probably a really, really, really good representation of what the population's like as a whole. So the bigger the sample you have, the less sampling error you have, the lower your standard error, and so on. So in general, like, it's not a perfect relationship, but in general, as your sample size goes up, as you get more and more people in your sample, the less sampling error you have, because you have more information about the population. So let's use an example. I believe a lot of stats classes use, like, colored marbles in a bag, but, you know, I'm a psychology and anime channel, so I figured I'd play around a little bit. Let's say we have a group of about 50 some anime high school students. 50 of them have black hair, 3 have brown hair, and 1 has blonde hair. Now let's say you randomly select 5 of these 50 students. If you only see 5 of these students, what do you think the hair color of the students at this school looks like? Well, because there's so many more students that have black hair, you'll probably assume that everybody at the school has black hair, because chances are all 5 of the students you randomly select will have black hair, because that's the vast majority of the students. Now let's say I'm still on the marbles thing. Let's say you randomly select 20 students. At that point, maybe you get a student with brown hair, and you might say, oh, okay, the majority have black hair, but there are some students here that also have brown hair. By the time you've pulled all 50 marbles, so you have the full population, you've probably realized, yeah, most of them have black hair, but you have some with brown hair and a very occasional student that has blonde hair. The more of the population you have, the more information you have, the better a picture you have and the less sampling error you have, the fewer things you'll miss. So the more people you have in your sample, or the more things you have in your sample, the more information you have, the less sampling error you have, the better. Long story short. Now let's talk about the standard error and the standard deviation and how those relate. So we've established bigger sample size means a smaller standard error. What about the standard deviation? Well, standard error, again, one of the things used to calculate it is the standard deviation. And the standard error is a special type of standard deviation. It's specifically the standard deviation of a bunch of means, whereas the standard deviation we learned before is just for a bunch of individual scores. you can calculate the standard error from the standard deviation and also from the variance, because the variance is used to calculate the standard deviation. Here's those two versions of the formula. Now, what do you think happens to the standard error when you have a bigger standard deviation? I'd like you to take a minute. Do you think it goes up or down? If my standard deviation's big, will my standard error be bigger or smaller? I'd also like you to think, if I have a smaller standard deviation, will my standard error be bigger or smaller? Well, we can calculate this out if we want to. I've given you some possible example standard deviations, but generally speaking, oh, these are all sample sizes, but generally speaking, the standard deviation is the numerator of the equation. The bigger your standard deviation is, the bigger your standard error will be. The more variability you have in your sample, the wider the variety of scores you have in your sample, the more sampling error you'll have. If your standard deviation is smaller, if you have less variability in your sample, everybody in your sample is pretty close to the sample mean, that means your standard error is going to come out smaller because the numerator of the fraction is smaller and you'll have less sampling error. So we can do this by, swapping out various standard deviations in this equation. We can also see the effect of sample size when we do this. So just to show you how the standard deviation and the standard error relate to one another, here's the formula for the standard error. Standard deviation over the square root of the sample size. What happens when the sample size is 1? Well, let's say, for the sake of argument, our standard deviation is 10, just the standard deviation of the promise score. If our sample size is 1, then we just end up, so the square root of 1 is 1, we just end up getting 10 back. If the sample size of each of your samples is 1, that's no longer a sample anymore. You're not calculating a mean, that's just an individual score. As your sample size increases, that's the point where it starts differing from the standard deviation, because you're no longer talking about individual scores, you're talking about means. So let's say I increase my sample to 64. Then we have 10 divided by 8, and we get some number. I'm not good at math. I cannot do this in my head. Please save me. 10 divided by 8. It becomes 1.25. So as your sample size goes up, first of all, as your sample size goes up, you can see your standard error goes down. When we increase the sample size from 1 to 64, our standard error has gone down. And if you don't have a bunch of samples, if you just have a bunch of individuals, your standard error is going to be equal to your standard deviation. Both the standard error and the standard deviation are just kind of estimates of how much error you have. They're both how much variability you have around the mean. Is everything close to the population mean, or is it more spread out? That kind of deal. All right, let's go back to sampling distributions. Sampling distributions, again, is when we have a distribution of sample means. So you've got a whole bunch of samples from a population, you get the mean of each sample on something, say their mental distress score, and then you create a distribution of all of those means. When we were comparing one person to a population, so last class we talked about z-scores. When we use z-scores to compare a single individual to a full population, I gave you the mean and standard deviation on some variable, whether it was promise scores or strength scores or whatever it was for individuals in that population. And you knew that the individual scores in the population were normally distributed. So we'd calculate a z-score and we could say, this is how unusual or typical this person is of the population. But now we are working with a distribution of means, not of individuals. So we need the same information now, but for a distribution of sample means, not for an distribution of individual scores. And what this will allow us to do is compare a single sample to the population and say, is the sample particularly unusual? We are going to need the mean of the distribution of sample means. We're going to need the standard deviation of the distribution of sample means, and the shape of the distribution of sample means. And if we have all three of these things, I can say this particular sample seems pretty typical of the population, or this particular sample seems unusually high compared to the population or unusually low compared to the population. So for example, let's say I get a group of 20 people. I know the population mean for mental distress on the PROMIS scale is 50. And then I make these 20 people watch the most mind-scarring anime that you have ever seen. And then I test their mental distress score. I can then compare their score on mental distress to the population to see if watching that horrible, horrible anime has made them more distressed than the general population. I can start testing hypotheses, is essentially what I'm saying. I can see if what I did to a group of people changes them from the population. So first, all of what I've said so far is assuming that you create a sampling distribution where you have a giant distribution of every possible sample from a population. But do you think that I, as a researcher, or any researcher, has the time and resources and mental strength to, get every single possible sample from the population? Do you think that, do I have to get every possible sample, or hundreds and hundreds of different samples from the same population every time I want to test a hypothesis? No, that would be crazy. That would be way too much. That would take way too much time, way too much money. We have much better things to do, and it wouldn't really improve. We can't get the whole population. What makes you think we can form a complete sampling distribution? Sampling distributions also require access to every individual in the population. It's just not possible. Now, luckily, there's some mathematical laws and rules about sampling distributions that means we do not actually need to collect every possible sample. We don't need to do that. We can just collect one sample and use that to estimate our sampling error. So that saves us a lot of time and money and work. Awesome. So what are these amazing mathematical rules that allow us to do this? Well, amazing rule 1, and you see some notation up here. The mean of a distribution of population mean, or of sample means, is the same as the mean of the population. So if I get a whole sampling distribution of sample means, every possible sample mean drawn from a population, and take the mean of that, it will be equal to the population mean. So the mean of a distribution of means is equal to the population mean. If I get a mean of the sampling distribution of all the possible samples for the PROMIS, it should equal 50, which is the population mean. Why? Well, whenever you draw a sample, it's equally likely to be to overestimate or underestimate the population mean. So it all averages out to the population mean. The population mean is essentially a balancing point. Half are above, half are below. Take the average, you're right on the population mean. Something like this. And we'll get to this a bit later, but it's related to amazing rule number 2, which is that the standard deviation of a distribution of sample means is the mean of the standard deviation of the population of individuals divided by the square root of the number of individuals in each sample, which sounds complicated, but it's literally just telling you the formula of standard error. It's saying, amazing rule 2, we can use this to estimate our sampling error. We can use this to estimate how different, on average, samples are from the population. We don't need the entire set of means to do this. We can just use this formula, which saves us a lot of time and resources, again, which is great. Now let's take another look at this. What do you think happens to the standard error of the mean as the sample size goes up? A little bit of review there. Keep in mind, this n at the bottom is sample size. So as this number on the bottom, the sample size goes up, what happens to our standard error? Does it get bigger or smaller? Well, as the denominator of a fraction gets bigger, your standard error gets smaller. Or your result gets smaller, in this case the result being the standard error. And that's what this is showing. It's saying, look, when the sample size is 2, the distribution is this wide. You have a fair number of people that are pretty far from the population mean. So there's your standard deviation of sample means, aka the standard error. But as we increase our sample size, the distribution of sample means gets narrower and narrower. Our standard error goes down and down and down to the point where, look at that, we have really reduced our sampling error. So this is just another bit of like the law of large numbers. The more people we have in our sample, the closer we're going to be to the population, the less sampling error we have. Which brings us to amazing rule number 3. The shape of a distribution of means is approximately normal, so the shape of a sampling distribution becomes roughly normal if either each sample is of 30 or more individuals, so your sample has at least 30 people, or the distribution of the population of individuals is normal. There are 2 ways to get a normal distribution out of this. Why? Well, even if you have a skewed distribution of individuals, let's say you're measuring reaction time, which tends to have a pretty positively skewed distribution. Most people react really fast, very few people react slower than that. Even if we have a skewed distribution to start, the more samples you draw, the more likely you are to balance out your outliers, and each time you're still half the time overestimating, half the time underestimating. It will become normal. Here's an example of the sample means for 1,000 different samples of 30 people each. You can see it looks pretty normal. This isn't the full population, but it has become fairly normal at the point where we have 30 people per sample in a lot of samples. We are pretty close to the population mean. So this allows us to say, if we have a sample, first of all, we can be fairly certain that our sample mean is most likely close to the population mean. It's probably not at exactly the population mean, but most samples should be pretty close to the population mean. And using this formula, we can estimate on average how off should our sample be from the population mean. And we can be fairly confident that the distribution of samples should be normal. So again, we can be fairly confident that our sample mean will be pretty close to the population mean. Even if we don't have all possible samples, even if we don't have population data, we can be fairly confident that our sample mean is close to the population mean. So we can use samples. We can justifiably use samples, especially because we have that measure of sampling error. We can use a sample, we know it's close to the mean, we know it's not exactly at the mean, but we can estimate how far off it is. Now let's talk about how standard error relates to reliability. So we talked about reliability. We may have talked about this before. Reliability is the consistency of a set of measurements or measuring instrument. Are you getting the same result every time you use it? High reliability, let's say, I think before I use the example of archery, high reliability would be hitting roughly the same spot every time. You're getting the same answer every time, or at least roughly the same answer. But there's another thing that we care about in statistics and research, and that's validity. Are you measuring what you actually want to measure? Measuring what you want to measure, so like, is your happiness measure actually measuring happiness? Is the PROMIS mental distress scale actually measuring how distressed somebody is? You can think of it in terms of like archery. Are you actually hitting the bullseye, or are you hitting like a tree off to the side? Reliability and validity are not the same thing. Just because a measure is giving you the same answer every time doesn't mean it's a valid measure. A stopped clock, so a broken clock or a broken watch that shows the same time all day, is very reliable. It will give you the same answer every time, but it isn't a valid measure of time because it's not measuring time. It's just displaying the same number. So just because something is reliable doesn't mean it's valid. Just because you're getting the same answer every time doesn't mean the answer is right. You can get the same wrong answer many, many times in a row. A reliable measure is consistent, but that doesn't mean it's necessarily measuring what it's supposed to be measuring. So for example, do you think standardized tests that you used to get into college are reliable after the first year of college? They're very reliable in that, yeah, they're reliable. You keep getting similar scores on the SAT. Do you think it is a valid measure of your performance in college after the first year? Not really. It doesn't seem to predict much college performance after the first year. So just because you have a reliable measure doesn't mean you have a valid measure. The standard error is a measure of reliability. It says, it's asking whether sample means are going to be consistent. If you get a whole bunch of samples, should they give you roughly the same mean? If your standard error for several sample means is small and consistent, then your samples are reliable. You have a good sampling procedure, your experimental procedure is good, you're getting roughly the same answer every time, regardless of what sample you use. If your standard error is large and inconsistent, that means your measurements probably aren't very consistent, or something's wrong with your sampling procedure. You're getting wildly different results every time you try and collect a sample. Of course, this does not suggest just because you're getting the same sample mean every time doesn't mean your measurements are measuring what you think they are. That's an entirely different question. So standard error is a measure of reliability, but it's not necessarily a measure of validity. You can have a study with a very small standard error that isn't a good study. Just because you have a small standard error doesn't mean it's a good study. But if you have a big standard error, there probably is a problem with your study. If you're getting very different numbers every time, even though you're doing the same thing every time, maybe your measure isn't that great. That's all I'm saying. Or maybe there's some problem with your experimental design that's causing differences other than your independent variable. Now let's talk about probability in these sampling distributions. Before, we were able to calculate the probability of randomly selecting somebody with a certain score by looking at their z-score. How far was their score away from the population mean? Now, we can find the z-scores of sample means as well. We can see how typical or atypical a sample is. Is this group of people like average, or is there something exceptional about this group? This is the formula for the z-score for sample means. The old formula was z is equal to a score minus the population mean over the standard deviation. This formula is very similar. In this case, we're not talking about an individual score, we're talking about a sample mean. So sample mean has replaced individual score. We're still comparing it to the population mean. We're still comparing it to the typical score in a population. And we've changed the standard deviation to the standard error. We've changed the standard deviation into the standard deviation of a distribution of means, which is calculated using this formula. So just some notes, yeah, again, x representing a single score has changed to m representing the average of a sample. The standard deviation, sigma, has changed to sigma of m, the standard error, because now we're dealing with sample means instead of individuals. And this can allow us to find the probability of randomly getting a sample with a certain mean. Now, what happens to this new version of the z-score equation if we change the sample size to 1? Let's find out. So essentially what I'm saying is, what happens to this new way of calculating z-scores if instead of using a bunch of sample means, I just use a single score, because that's one person? Well, let's see. If the sample size is 1, that's the standard deviation over the square root of 1. That just gives me the standard deviation again. If I plug that into the z-score formula, I'm no longer working with an m. This is no longer a mean, because I only have one person. Minus the population mean over, we calculated the standard error to be equal to the standard deviation. You can literally transform the z-score for a sample mean into the z-score for an individual when your sample size is 1. That's what happens. If you only have one person in your sample, it just switches to the type of z-score we learned about before. Now, because we can estimate how far a sample is from the sample mean, we can do what we did with the z-scores before. We can say, how likely is it that I just grabbed 60 random people that happen to have this sample mean? How likely is it that I just happen to grab 60 people who are incredibly low on mental distress or incredibly high on mental distress by chance? So let's do an example. Let's say I want to make a video game that decreases people's mental distress. There are people out there who are working on video games that are supposed to be therapeutic. So let's say I'm one of those people. I give a class of 20 students my mental health video game trademark. Afterwards, I give my students this promise mental distress scale. Now, there's 3 alternate universes here, there's 3 AUs here, 3 possible outcomes. And let's say, what's the probability of getting any one of these means from the population by chance, where the population mean is 50 and the population standard deviation is 10? So let's start with AU1, alternate universe 1. What is the probability of getting a mean of 53? So first things first, let's look at this formula. If you're not sure where to start, look at the formula. Do we have enough information to just start from this z-score formula? Well, we have the population mean. The population mean is 50, so we have this. We have the sample mean. The sample mean in this case, we're using the example of 53. But we don't have the population standard error, so we need to calculate that first. Here's the formula for standard error. We do have the standard deviation of the population right here, 10. We know that for the promise because it's a standardized measure. And I've told you that the sample size is 20. So let's start here. Let's start by calculating the standard error. And this is the example we're using. The standard error for this particular sample is the standard deviation of the population, 10, divided by the square root of the sample size, which was 20 people. So let's take the square root of 20. Boop, 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 boop. So that is 10 divided by 4.47, rounding to 2 decimal places. We divide 10 by 4.47. 10 divided by 4.47 gives us a standard error of 2.24 about. Now that we have that, we can calculate the z-score. So z is equal to our sample mean minus the population mean over the standard error. Our sample mean in this particular version is 53 minus our population mean, which is 50, over our standard error of 2.24. 53 minus 50 is 3, over the standard error of 2.24. 3 divided by 2.24 gives us a z-score of 1.34. This sample mean is 1.34 standard deviations above the population mean. This sample is more mentally distressed than the population. Now let's think back to the rules that we set last time. We start to consider a score unusually high or unusually low, significant, you could say, if it is more than positive 1.96 standard deviations from the mean. A z-score represents how many standard deviations you are from the mean. So, in this case, the mental distress score is 53, which is 1.34 standard deviations from the mean. For us to consider this sample significantly different from the population, again, the z-score has to be more than 1.96 away from the mean. But this is not. This is closer to the mean than our cutoff of 1.96. We would not conclude that this is a particularly unusual sample. It's within the margin of error, you could say. In this case, we would not be able to conclude that my mental health video game changed this sample's mental distress. Let's try the second universe. So let's say we've gone over to another universe, or maybe I've updated my game. And I want to, and this time I get a mean on the mental distress scale of 46. We don't have to recalculate the standard error because the standard deviation of the population has not changed and my sample size hasn't changed, so we can just keep that 2.24. The only thing we need to change is the mean that we plug in. The sample mean is now 46. 46 minus 50, we are 4 points below, so we get -4, we're 4 points below this population mean. Then we do -4 divided by our standard error of 2.24. Our z-score is -1.78. So this time, our sample is 1.78 standard deviations below the population mean. So our sample is about here. They are less mentally distressed than the population, so that's great. But they're still within the margin of error. They are not beyond that cutoff of negative 1.96 or positive 1.96. We cannot conclude that we did anything special to the sample, or that this mental distress video, that this mental health video game changed the sample at all. We can't. It doesn't work. This is still within the margin of error. We could have still gotten this result by chance. I can't conclude that my mental health video game improved players' mental health. So essentially, like I said, we can use this to start testing hypotheses to see if doing something to a sample makes that sample different from the population. So let's connect some ideas. The logic of the z-score is still the same. We're still saying, how different is this thing from the population? Is it particularly unusual compared to the population? We're still looking at essentially the probability of getting a single value from a population distribution. Before, we were saying, what's the probability of, say, picking a random person off the street given the population distribution? Now we're saying, what's the probability of picking a group of people off the street and getting this mean compared to the population? Instead of a single score, though, how do I use y equals mx plus b on this? Slopes. We'll get into slopes later. We'll get into slopes when we talk about correlations. Sorry. But yeah, now, rather than just comparing an individual to a population, we compare a group of individuals to a population. We can compare a sample to a population and see if that sample's particularly unusual or if it just seems typical. The strength and weaknesses of the mean as a measure of central tendency still apply. So this is only really useful if the population distribution is normal, if, if most people are close to the population mean, or if most people or most samples are close to the population mean, very few are far away, and half are above, half are below. If you've got a very skewed distribution like this doesn't work so well. This is z-scores with a very skewed distribution, like if you're doing the z-score of reaction time or something like that, this isn't great for that. Z-scores, because the mean is less representative of a distribution, if the distribution is heavily skewed because it's being pulled out to the tails by those outliers, the z-score is a lot harder to interpret if you're working with a very skewed distribution in either direction. So z-score is not recommended for this. So yeah, again, mean is not an accurate representation of the sample in a skewed distribution. So take z-scores with a grain of salt if the distribution's skewed. All right, let's review some ideas real fast. Which sampling distribution, A or B, contains the most sample means? First, what is the default shape of a true, like let's say you have a full sampling distribution. What's the shape of a sampling distribution? It's normal. The more samples you get, the more sample means you get, the closer to a normal distribution your sampling distribution should become. So that means the answer is A. A looks the most like a normal distribution, so it is the distribution that contains the most sample means. All right, let's do one more bit of review. This isn't something that I've taught you directly, but if you pay attention to the formula for the standard error, you should be able to figure this out. So let's say I have 3 samples here, sample 1, sample 2, and sample 3. Again, little n is your sample size, that's how many people are in the sample, and SD is your standard deviation. So little n is this bit, SD is this bit. Which sample, sample 1, sample 2, or sample 3, do you think has the least sampling error based on this information? Well, first things first, we know that bigger sample sizes lead to a smaller sampling error. So, first, let's look through these sample sizes. The sample size of sample 1 is 100, sample 2 is 100, and sample 3 is 200. So that's already a good sign. We know a bigger sample size leads to less sampling error, and sample 3 has the biggest sample size. But that's not the only thing that affects it. We also know that a smaller standard deviation leads to less sampling error. You know, it's the numerator of the equation. So if it's a smaller number, the result will be smaller. Sample 1 has a standard deviation of 5, sample 2 has a standard deviation of 30, and sample 3 has a standard deviation of 5. So 1 and 3 both have the smallest standard deviation. So essentially, to answer this question, we are looking for the combination of the biggest sample size with the smallest standard deviation. We could do the math and find the smallest standard error, but we don't have to. All we need to know is say, wow, sample 3 has the biggest sample size of all 3 samples and the smallest standard deviation of all 3 samples. Therefore, sample 3 would result in the smallest standard error. It would have the least sampling error. Because remember, standard error is an estimate of how much sampling error there is, how far off our sample is from the population. Oh, all right. If y'all have any questions, I am happy to take them now. Let's see, I will count. I know there's a delay in chat, so I will count in my head to 20. See if there's any questions in chat by the end of that. And if there are not, then I'll end the stream there. And if you have any questions, you can leave them in the comments section of the VOD. All right, counting start. Okay, so that does it. It looks like that's the end of the lecture for today. Thank you all for coming. I hope that you have a lovely day, and I hope that this was helpful one way or another. And again, if you have any questions, leave them in the comments section, and I will get to them as soon as I can. I will see you next class on Monday, and that will be the last class of this batch of lectures. And there will be a several week or maybe even several month break in between lectures, depending on how long it takes my job at my other university to calm down. And then I'll get back to it with some new material. Monday is going to be talking about hypothesis testing. And then after the break, we'll come back in with t-tests. All right, everyone, take care, and I will see you next class. Bye.